Hi Pete, this is Group Three's video project.
For our project, we decided to take a video of me jumping. So here's a video. So as you can see, we start from a standstill and I go into a squat where I start applying force against the ground, which accelerates me up into the air, up to a maximum vertical height. So as we're looking at our jump, we initially look at through the momentum lens, and we know that momentum must always be conserved. And so while looking at my jump, we understand that the impulse imparted onto my body as I jump is equal and opposite to the impulse imparted on the earth, meaning that the two have equal and opposite impulses, which would then conserve momentum when added together.
When we look at the jump through the kinematics lens, we know that all of our graphs are going to be derivative of the position that we find. Our position versus time graph comes straight from our tracker data. And then we get the velocity from the slope of that graph and the acceleration from the slope of the velocity graph, as you can see here. And as you see, we have our position versus time graph on the left, which turns into our velocity versus time graph, which we simplify just because errors in position make it essentially too volatile to look at and really analyze for acceleration. And then from our simplified velocity graph, we can find the acceleration.
So for the dynamics lens, I set the red arrow to be the force of normal and the white arrow to be the force of gravity. So in the first picture, you can see Jackson is standing still, so they will be equal to each other. In the second picture, the force normal will be greater, therefore giving him an acceleration upwards. It will be greater than the force of gravity arrow. In the third picture, when Jackson is coming back down, there will be no acceleration except for the acceleration of gravity, which is just a white arrow, which will carry him back down. So in terms of energy, we believe that this was the best lens for this project, for we can clearly see the transfer of energy from Jackson's chemical potential energy to the transition of kinetic energy right from the moment he jumps off the ground to the gravitational potential energy at his max height, then back down to full kinetic energy right before he hits the ground. And as he hits the ground, all that energy disperses into the earth. So with the raw data, we were able to graph the mechanical energy, which is the total energy graph, the kinetic energy graph, and the potential energy graph, as you can see right here. And then we smoothed it out with this graph right here. With these transitions in energy, we were able to calculate power.
All right, so for finding the power, we can see this total energy versus time graph, and we can calculate power from the slope. So the total energy trend is from 0.7 to 1.1 seconds, and that's when the most power is exerted because this is the time when his feet is pushing downward on the ground to when his feet leaves the ground. And so in order to find the power, we take the change in energy over the change in time, which is 737 joules minus 0 divided by 1.1 minus 0.7, and we get a power output of approximately 1,842.5 watts, or about 2.5 horsepower. After this time range, the power is 0 because he is no longer exerting force and he leaves the ground.
Finally, as we look through our project, we understand that there may be a couple of areas that have some inaccuracies in our calculations. The first is looking at our graphs. We derived all of our graphs from our position versus time graph that came off of tracker. And so the little blips that came out of the inaccuracies on that graph were then carried on through the derivations into the other graphs. We helped solve this issue through hand drafting the rest of our graphs. The angle of the camera lens also played a small part in the inaccuracy of the measurements. It's because it was tilted just a little bit so that the measurement of angles when we used the measuring stick was not completely true to the actual height of what we measured. And finally, my head moves faster than the rest of my body as I go through my jump, which results in a higher than what we would have expected to see kinetic energy, which then creates more power output than what we actually made. But we understand that these were our inaccuracies, and that was our project.